one slight downside to this in this place of this chapter. So if you look at the definition, it's spontaneity, entropy, and free energy. This is where change in G comes in. I don't know if you guys remember that from the dreaded equilibrium chapter that was in regular chemistry. It has really two factors in it, the enthalpy and the entropy. And I think it was chapter 5, maybe chapter 6, where we did thermodynamics. We did change in H, that whole chapter. So there will be some stuff we will talk about from that chapter. There will also be some stuff that we'll talk about from the kinetics chapter, because to understand spontaneity, we've got to understand both thermodynamics and kinetics. And that's kind of what the introduction of this is getting at. So, do you guys remember the first law of thermodynamics? Okay, energy and what? Matter. Now we're going to focus on the energy portion of that today. Matter and energy cannot be created or destroyed, but can only go from one form to another or change forms. In other words, if you were to redefine this law or to give it maybe a simpler definition, you would just say the energy in the universe is constant. When I say the energy of the universe is constant, what does that mean?
It doesn't atoms or factors, it's the same.
Okay. Well, when you say stays the same, you mean amount, right?
Yes, the amount.
Can it change from one form to another?
Yeah.
Could it go from a usable energy to an unusable energy?
What
What?
is sound unusable energy? What's
Well, it depends. It's unusable for the system you're talking about.
Oh, okay.
Right, because sound might be usable in certain situations, but if you were wanting to figure out kinetic energy, losing some of it in the form of sound would not be ideal for that situation.
Okay.
Does that make sense? Okay? All right, so the total energy in the universe is going to be constant. Okay, so an example of this, when you have an exothermic reaction, what does that mean?
What energy leaves?
Energy leaves. Well, where did the energy come from?
The bond.
The potential energy stored up in the bonds. Okay, in the end, did I have the same energy at the beginning and at the end, same amount of energy? Yes, but did it change from one form to another? Absolutely. Okay, so when we talk about the first law of thermodynamics, it's really just an energy bookkeeping system to make sure that we have the same energy at the beginning as we do at the end. How much energy change did we have? Was the energy flowing into the system or out of the system? What was the form of the energy? Those are a lot of the questions that we used first law of thermodynamics to help us understand. Okay? Now, although the first law of thermodynamics provides a means for accounting for energy, it gives no hint as to why a particular process occurs in a given direction. Okay? So although it tells us how much energy change there is, it doesn't necessarily tell us why. Okay? Now, when I use the word spontaneous, what does that mean?
It happens without intervention, I guess. Without being
Yep, a process is said to be spontaneous if it occurs without any help. That's pretty good, actually, for not reading.
I remember remembering from the chemistry class, I was doing a test during that chemistry class.
Oh.
It was over this.
Oh, okay, yeah. So when I say something is spontaneous, I mean that it doesn't need our help, essentially. Okay? Now, if I say something spontaneous, does that really tell us anything about how fast? No.
Diamond
Yeah, so that's actually what we were going to read about.
Oh. Sorry.
It's okay.
I tried to say nothing.
I don't know if you guys remember this, but thermodynamics is path independent and kinetics was path dependent. Okay? This is a while ago, so this is a review here. Okay? Do you remember when we were doing enthalpy? We usually did products minus reactants, correct?
Yeah.
All we wanted to know was the difference in energy from the beginning and the ending. Didn't matter what the path was, wasn't important. Kinetics is when we start talking about activation energy. And we start talking about how fast, rates. That was path dependent. Wanted to know what happened along the way. So if you flip the page, there's just a little graph, an energy graph, and it kind of highlights the part that is kinetics driven and the part that is thermodynamics driven. is the purple or the blue, purple or the green, the kinetics part? Purple, the path. The green part is the beginning and the ending. You put them two together, it can tell you a lot, spontaneity. But we need both, along with what we're going to talk a significant amount about in this chapter, which is entropy. I'm going to start reading in summary underneath that graph. Okay, it says in summary, thermodynamics. This is good because it's been a while since we've done thermodynamics, and it's been a while since we've done kinetics, so a good little review summary here. Thermodynamics lets us predict whether a process will occur, but gives us no information about the time required for the process. For example, according to the principles of thermodynamics, yes, Rylan, a diamond should change spontaneously to graphite. The reaction of diamond breaking down into graphite is a spontaneous one. What do I mean when I say it's a spontaneous one?
It's happening.
It's happening. Doesn't need our help. Okay? The fact that we do not observe the process does not mean that the prediction is wrong. It simply means that the process is very slow. Thus, read both thermodynamics and kinetics to describe reactions fully. Read both of them. Okay? To explore the idea of spontaneity, consider the following physical and chemical processes. A ball rolls down a hill but never spontaneously rolls back up. If exposed to air and moisture, steel rusts, but iron oxide in rust does not spontaneously change back to iron and oxygen gas. A gas fills a container uniformly, but never collects in one end of the container spontaneously. Heat flows from a hot object to a cold one, never reverse. Wood burns spontaneously in an exothermic reaction to form carbon dioxide and water, but wood is never formed when carbon dioxide and water react. Yeah, right?
It's super dangerous because you like
Okay.
exhale underwater and just
Turn into a block of wood.
bounces forward. Stuff.
As temperature below 0 degrees, water spontaneously freezes. At temperatures above 0 degrees, ice spontaneously melts, never the opposite. So what thermodynamic principle will provide an explanation of why, under a given set of conditions, each of these diverse processes occur one direction but never in the reverse? In searching for the answer, we could explain the behavior of a ball on a hill in terms of gravity, but what does gravity have to do with the rusting of a nail or the freezing of water? Early developers of thermodynamics thought that exothermicity was the key. What they mean by that is, they thought the driving force of a spontaneous reaction was based on if it was exothermic, because exothermic means it was going to be lower energy and therefore stable. That makes sense, right? From an earlier standpoint, without knowing all the little details, that would be a good prediction. Okay? Thought exothermicity was the key, that the process would be spontaneous if it were exothermic. Although the factor does appear to be important, and yes it is, since many spontaneous processes are exothermic, it's not the total answer. For example, the melting of ice, which occurs spontaneously at temperatures greater than 0 degrees, is an endothermic process. Energy's coming in. Okay? What common characteristic causes the processes listed above to be spontaneous in one direction only? After many years of observations, I find this interesting, this is a secular textbook, scientists have concluded that the characteristic common to all spontaneous processes is an increase in a property called what? What is entropy?
Disorganization.
Going from order to disorder. If things want to happen spontaneously, the secular textbook here says, the only thing that they have seen common to all spontaneous reaction is an increase in entropy of the universe. Seems odd. So what is entropy? Okay, entropy is viewed as the measure of molecular randomness or disorder. The natural process of all things, just right out of the secular textbook itself, is from order to disorder, from low entropy to high entropy. To illustrate the natural tendency toward disorder, we only have to think about the conditions of your room. Your room naturally tends to get messy because An order room would require everything to be put in its place. There are simply way more ways for things to be out of place than to be in place. Right? Is there 1,000 more possibilities to be out of place than to be in place? There's only one possibility for it all to be in place. Naturally, if it has more possibilities to occur, it's likely going to occur that way. Another example, suppose you have a deck of playing cards, ordered in some particular way. You throw these cards in the air and pick them up at random. Looking at the new sequence of cards, you'd be very surprised to find that it matched the original order. Obviously, common sense tells us this. Now listen to this. It says such an event would be possible. It's possible, right?
I think it's the same chance as every other individual order.
Yeah, technically.
The rest of them add up to be.
But if you're looking at one chance versus the chance of having all the other chances.
Right, this or
Yeah.
not this, instead of
Yep.
this or this order.
There are billions of ways for the deck to be disordered, but only one way to be ordered according to your definition. Thus, the chances of picking up the cards in order are out of order are much greater than the chance of picking them up in order. This is the idea of entropy. Entropy is a thermodynamic function that describes the number of arrangements or positions that are available to a system existing in a given state. If you have more positions, it's going to be more favorable. If you have more possibilities, it's going to be more favorable. Okay? There are way more possibilities to have a dirty room than a clean room. Okay? The key concept is that more ways a particular state can be achieved, the greater likelihood or probability of finding it in that state. Do I have that written down somewhere? Because that is important. Do you have that? You guys have that anywhere?
There are more ways a particular state can be achieved, the greater difficulty.
Do you have that? Yes. I would, that's the one I would make an important note on. Is it on the next slide? Yes. Okay. So the driving force of a spontaneous process is an increase in entropy of the universe, from order to disorder, and the reason why is this. The more ways a particular state can be achieved, the greater probability it's going to be in that state. This is why when a gas is in a container, it's more likely to be randomly everywhere than to be over and hanging out in the corner next to each other. Is it possible if I took a picture at one point that all the particles could be over in one little corner? It's possible, but extremely what? Unlikely. So the idea here is the higher the number of states you could have, the more likely to be in that state. Okay?
So, do you think entropy was caused by sin, or do you think it was God who created it? Because some entropy is harmful, but a lot of it isn't. Like some entropy is decay, like rusting is decay, but gas particles moving around randomly isn't decay. It's just
That's a great
useful.
question. What do you guys think?
Did entropy become corrupted?
Do you think
Like,
it's because of sin?
bacteria were around, like, well, it's not
Well, yeah.
think so.
What do you mean?
Like,
In the garden?
Before the fall, yeah, like not harmful bacteria, but
Oh.
help with digestion, and like things that some bacteria are good for
Sure.
the soil.
Sure,
It's
sure,
saying
sure.
that they became corrupted is what I think is what Saffron says. I don't know if he's right, but it seems.
So you're saying we had a lot of these same things, but because of sin, they became.
Right.
That makes sense.
Well, because it was work, but it wasn't painful work. Like because God would say your work will not be hard and painful, and
Yeah.
but I don't know.
I wonder what that was like.
Like just no muscle tiredness. You just like plow fields for 8 days solid.
Yeah, I don't know. That's always an interesting thing to think about. But yeah, I would assume that the human body at that point wasn't right. It didn't deteriorate.
Right.
Right. Even if you look at the biblical age of people early on,
Yeah.
right, they were living 600, 700, 800 years
Genetic
easy.
entropy. What causes people to age to death is a lot of random mutations that affect your organs and stuff.
That happens over.
That happens in the lifespan. So I'm assuming, I don't know, for sure maybe more resistance. But or there's less genetic entropy. It's really interesting.
I would say yes. I would say before, if I were to take a guess, I would say before sin, entropy was not a thing.
But then gas particles are just collected in the corner then?
Good question.
Yeah, because or put it back. Just go
Maybe there was good entropy, but not bad.
Yeah, I don't know.
Otherwise you
There's no way of knowing
you
for
pour
sure, but
sugar-
it's an interesting topic.
You pour
to
the
think
Kool-Aid
about.
powder into your water, it just sticks to the bottom of the next.
Okay, I want to turn to the next page. The book talks about microstates. Basically, what a microstate is one of the particular ways. Does that make sense? So like, if you have a probability, if you have a lot of potential states, each state is a microstate. So if there are a bazillion ways to arrange a deck of cards, one of those arrangements would be called a microstate. Does that make sense? Okay, so if you look at this chart, and let's look at table 17.1. Okay? It's saying, if you've got 4 gas particles, arrangement 1, could you have all 4 gas particles on the left? Absolutely. Okay, but there's only one arrangement where they all will be on the left. And if you look at the very bottom one, the same thing would be there's only one arrangement where they're all going to be on the right. Okay? So one microstate for both. In arrangement 2, where you have 1 on one side and 3 on the other, there are 4 possibilities of that. A being on the one, being alone, B being alone, C being alone, and D being alone. 4 possibilities, 4 microstates. So from a sheer probability standpoint and from an entropy standpoint, the most likely arrangement of those 4 gas particles is what? What's the most likely arrangement? Well, I know. Which one has the most microstates? The third one, right? That one has 6 possibilities of it being 2 on each side. So most of the time, you're probably going to see 2 on each side. It's the most likely possibility. Does that mean it's the only possibility? No, but it is the most probable due to sheer probability. Okay? And we will talk about a little bit later how volume plays a big part in probability. So, positional probability. Okay, so type of probability depends on the number of arrangements in the space that yield a particular state. Solids are more ordered than liquids or gases and thus have lower entropy. The tendency to mix is due to the increase in volume available to particles of each component in the mixture. So for example, the reason why salt dissolves fairly readily in water is twofold. Yes, there are some attractions, but are there more positional probability or more states it could be in, more randomness it could be in versus being really close to each other in the solid form? Okay, breaking apart, being distributed through the entire volume is far more likely. It's a messy room versus a clean room idea. Okay? So, we're starting to see that one of the reasons why chemistry is so difficult is to really understand big picture. There's a lot of little things that you have to understand. Thermodynamics tells us a lot, but it's not the only picture. Kinetics tells us a lot, that's not the only thing. Spontaneity tells us a lot, that's not the only thing. But if you take thermodynamics, kinetics, and spontaneity, and you put them all together, you can describe a lot about a chemical reaction. Okay? And that's where the difficulty in chemistry lies, is one thing isn't the only important thing. Okay? Let's do a couple problems. We'll see if we can. I mean, these aren't overly difficult. It says for each of the following pairs, choose a substance with the higher positional probability. First one's pretty easy. Yeah. What do you guys think? Yes. What number 2? This one more difficult, not extremely difficult.
Volume the same.
Well,
You have more,
no, the volume won't be the same because the pressure is different.
well, there's more room
What does pressure have to do with more, or
Well,
what is it?
it is amount of gas being held constant.
Yes, okay, so I'll say the amount of gas I have here is constant, don't leave.
Okay.
Okay, it's in a container. The volume is not constant. The volume depends on pressure.
Yes, I mean,
So based on high pressure, low pressure, which one has the greater volume? Low pressure. So this is going to have the higher positional probability. Lower pressure means more volume, which means more positions. The bigger the volume, the more potential positions you can have. Okay, last one here. I do want you to write this in. I know you guys are ready to leave, but I do want you to write, you should remember this. Positive change in S, negative change in S. Increase entropy, decrease entropy. So what does an increase in entropy tell you?
Less organized.
Okay, or more disorder. Less order or more disorder. A negative change in S means that entropy is decreasing. This means I'm becoming more ordered or less disorder. From that, you should be able to tell what the sign of this is. Solid sugar is added to water to form a solution. Is that more order or less order? Less order. So what would be your sign? Okay. Here it says vapor condenses to crystal. So basically a gas down to a solid. Order or less order? More order. That would be negative. Would be a negative change in S, that would be a positive. All right, done. Come on in.